Okay, so where did we stop last time? In the middle of something, right? In the middle of this. So we are proving the following theorem. The theorem is the following. Let me recall it again. So if T is a symmetric operator, unbounded symmetric operator, that is, it means T is contained in T star, which is equivalent to saying X T X T Y is equal to Txy for all xy in domain of T. Then the following are equivalent. 1, T is self-adjoint, T is equal to T star, and that is equivalent to saying for all Z in C minus R, kernel of T star minus Z equal to singleton 0, which is equivalent to saying there exists a Z in C minus R such that kernel of T star minus Z equal to kernel of T minus T star minus Z bar equal to 0. Okay, I mean these two for all Z in, and similarly 5 is there exists a Z such that the same thing happens. Okay. For all C minus there is a range of T minus Z equal to H. I mean for Z bar also it opens. No. So here it should be for all Z in, let me just write it better, right? Because we need it for the bar also. C minus R range of T minus Z equal to H is equal to range of T minus Z bar. Okay, when I write R, it means range. I may write capital R, I may write small r. R of something means range. Okay. So we have already proved 1 implies 2, 2 implies 4. So of course, for the same Z, the same proof occurs 3 implies 4 or I mean whatever. Okay, 2 will implies 4, 3 will imply 5. Okay, the same proof will work. You only need to prove. We are only left with proving 5 implies 1. We already know. So for that, we only have to prove. We already know that T is a symmetric operator. We have to prove it is self-adjoint. So we have to prove that. So it is enough to prove. We only need to prove. Domain of T is equal to domain of T star. Okay. It's already a symmetric operator. We only need to prove the domain of T equal to domain of T star. Okay. So let Y is in domain of T star. Okay. Then we have to prove that Y is in domain of T. Okay. Then, so since range of, so I mean there exists Z. So we know that range of T minus Z equal to H. There exists a X in domain of T such that T minus Z acting on X is equal to T star minus Z. This is some element Y. Okay. Y is in domain of T star, Y is in domain of T star minus Z. So this T star minus Z, Y, that is some element, and there exists, I mean, since for everything that is true, T minus Z X equal to this. There exists some X such that this happens. Okay. Now T, so now the domain of T is contained in domain of T star. Okay, so Tx equal to T star X, right? Since T is contained in T star as operators. Okay. So this implies we have T star minus Z X is equal to T star minus Z of Y. This thing implies that X minus Y is in kernel of T star minus Z. But that is equal to range of T minus Z bar. But then T minus Z bar is also H. So this is equal to 0. So this implies X equal to Y, which implies Y is in domain. Done. Full. You can just click a photo, whole proof is here. You need not write it. Okay. Whole thing is here. Surprisingly, I have written it clearly also. Then just handwriting is clear, I think. So you can just click.
Last time we started to read something.
Yeah, it's in the middle of that. 5 implies 1. 1 is to prove that it is equivalent to T is equal to T star. 5 implies T equal to T star for a symmetric operator T. Okay, and this is the whole proof. It starts here. Okay, you can either write it or look at the video later, or just click it. Okay. So we have proved this. Okay. Now we want to make, so once this is okay, shall I go to next topic? Okay. So we have proved this. This is direct. Now we want to define the spectrum and resolvent for the unbounded operator. So if you look at my earlier videos, there I have talked about spectrum, all these things for normal, bounded normal operators, and we have, the proof of the spectral theorem is there. Okay, we will assume that and prove spectral theorem for unbounded operators. Okay, so definition. So T is an unbounded operator. What do I say? Yeah, T is an unbounded operator, or whatever. T is a closed operator. Let us take a closed operator. Sorry, yeah. The T is a closed operator. We want to define these things for a closed operator. Okay, it need not be self-adjoint or something. Then define rho of T, which is called the resolvent, equal to all those Z in C. That's that kernel of T minus Z is trivial and range of T minus Z equal to H. So T minus Z is a 1, 1 on 2. Okay, but its domain is domain of T. Okay? Its domain is not everything. So if Z is in resolvent set, Z is in rho of T, then you can define T minus Z inverse from H. Okay? Which of course lands in domain of T, doesn't matter. This is well defined. Okay. And T, since T is a closed operator, T is closed. T minus
If Z is in rho T, then
T minus Z inverse makes sense. There is an operator. It exists. Okay? I just want to say it exists. Okay? Inverse exists. Algebraically, inverse exists. Okay? As a function, inverse exists, which is of course a linear operator. And T is closed, then T minus Z inverse is also closed. Okay? This is because if this XTX, X in domain of T, is closed, then TXX, right? That is the, that is the XT inverse is TXX, okay? Where again the same thing, X in domain of T is also closed, of course. You are just flipping, and that's a continuous function, 1, 1 function, and it's an inverse image of closed. Okay. So this is also closed. So closed graph theorem. My problem is I tend to write fast and then my handwriting becomes like this. I can't write slowly. Then closed graph theorem implies T minus Z inverse is bounded. Okay. So T is unbounded, but then T minus inverse, T minus Z inverse, okay, which is a bounded operator. So this operator is called the resolvent operator. We will not use this, but I am just telling you, is the resolvent operator. I mean, for Z in rho of T, we can define this. Okay. It's the resolvent operator, which is a bounded operator. It satisfies some resolvent equation and all that. If needed, I will come back. Okay, for the time being, I'm not doing this. Then sigma of T is equal to, it's just the complement. It's just the complement of rho. So the corollary of the earlier theorem is T equal to T star. Of course, it's closed, so we can talk about resolvent. Then sigma of T is contained in real line. That's what this is. Okay. The earlier theorem says that if T has an imaginary part, C has a non-trivial, non-zero imaginary part, then kernel of T minus Z and range of T minus Z, which is equal to kernel of T minus Z bar. I mean, kernel of T star minus Z, which is equal to range of T minus Z. And range of T minus Z bar equal to kernel of T minus Z, T star minus Z bar. Both they are, I mean, there are two things, no? One, this is the range of T minus Z, and range of T minus Z bar means, yeah, and we also have kernel of T minus Z, T minus Z bar, that's also equal to 0, which is equal to, what do you want to say? So range of T minus Z, if Z has an imaginary part, range of T minus Z is everything. And kernel of T minus Z equal to range of T star minus Z bar, no?
So if it's not a real number, it will be in the result.
Yeah, if it is not a real number, it's in the resolvent.
Yeah, that's what we're doing.
Yeah. No, not just we have shown. We have shown that for all Z, we have shown that for all Z, which if it has an imaginary part, that is in the resolvent. That's what you have shown, right?
Yeah, so what is it? C minus.
Yeah. If it has a non-zero imaginary part, that's what we have shown, right? Okay. So because of that, I mean, it may be to show some real numbers are also maybe in the resolvent, but sigma of T is contained in real number. That much is true. Okay. Okay, so that's what I want to say. Okay, now let's prepare for the spectral theorem. Okay, for that we have to define some operators. Okay, so I have already told you something about spectral measure, spectral projection, spectral measures and that. Okay, I will recall that. Okay. So definition. So omega script f be a measure space, measurable space. Measurable space means you can define a measure on that. Then P from omega to projections on H. Okay, these are projections on H. Is a spectral measure. Measure if P of whole omega is 1, P of empty set equal to 0, P of disjoint union. For this, I mean disjoint union. En intersection em is empty if n not equal to n, n equal to 1 to infinity, equal to summation n equal to 1 to infinity, P of en. P of en's are projection. So this is strongly. This is an infinite series. So that should converge to that in the strong sense. This is a set which is well defined. P of that set is well defined. Okay. And these are all these sets are measurable sets. They are all in ENs are in script F. They are in the sigma. Okay. Okay. So it's additive. It's an additive function, set function. But the value, it takes values in projection. So similarly, it can take values in complex number. That is what is called complex measure. Okay. We haven't done complex measure in the other course also. But if you want, you can look at those videos which are there or you can read the book, of course. So where complex measures are discussed. Okay? So this is what is called a spectral measure. And so given a spectral measure for if P is a spectral measure, I forgot, sorry. This is not correct. You should correct me. This is from script F, not from omega. That function is from script F, not omega, right? It's a set function. It's not on omega. Okay. So if we have a set function, omega to projections, okay, then mu xy, okay, equal to maybe mu yx. See, we are using conjugate linearity in the first variable, linearity in the second variable. It doesn't matter most of the time, but we should remember that when we do this. Usually in maths, it will be the other way only. But since we are doing quantum probability, we have to remember that. Okay, so I'm writing it, which is equal to y equal to y p of e x. Okay, is a complex measure, which is very clear. Okay. Since projection is additive, this will also be additive as complex numbers. We are just using one variable, which is linear. So this is a complex number. Okay, you can put P of E either side because it's a projection, self-adjoint. You can put it whichever the way you want. And mu of xxe is equal to P of E x, which is also equal to norm of P of E x square. So norm is not an additive function. Norm square is not a additive function, but here it's additive because when you insert the P of E, which is a projection, here it's additive function. As a set function, it's additive. Okay. So, okay, is a positive measure. I mean, usually what is called measure. It's a measure. Okay, for which we have integration theory and all that. You can define integration theory for complex numbers also, complex measures also. Okay, and we have mu xx of whole of omega is equal to norm x square. If norm x square equal to 1, then it's a probability measure. Okay. So this is about spectral measure. Okay. Now using this spectral measure, we want to define operators. Okay. For that, but we want to define unbounded operators. Okay. So definition. F from omega to C be a measurable function. I mean, you can integrate real functions. You can integrate complex function also. You just integrate real part and imaginary part separately and add it. Okay. So there is no problem with integrating complex functions. Okay? Be a measurable function. Then you write df equal to all those x in h such that integral mod f square. And you have this, for each x, you have this positive measure. Okay. Square is less than infinity, is integral. So all those x for which this f is square integrable with respect to that positive measure. So you call it as df. Okay. On this df, we want to define an operator, okay, unbounded operator. So if f is a bounded function, this is a finite measure, then this is true for all x. Okay. So note df equal to h if f is bounded. Okay. So lemma. I haven't called anything as lemma, so I will call this as lemma. Lemma. F is measurable. I mean, we have all the notations as before. Then df is dense. Dense and h. And DS is a dense subspace. Okay, let's say subspace. We have because we have to prove it's a subspace also. Is a dense subspace of which. I mean, a priori it's not clear, it's a subspace. So we have to prove that. So if X and Y are in DF, okay, then mu X plus Y E for some set E
X plus Y means X plus Y comma X plus Y.
X, no, yeah, X plus Y comma X plus Y, correct. Yeah, the measure corresponding to X plus Y. Okay. And this is a and this is equal to norm of P of E plus Y square, right? And which is of course P of E X plus P of E Y, which is I want to get 2 times that. So which is less than or equal to P of E X plus P of E Y norm square, of course, triangle inequality. Okay. Which is less than or equal to P of course, the first term P of E square, P of E Y square plus 2 times, it's all positive. So that is less than or equal to the square, of course. So which is equal to norm P of E X square norm Y square. Okay, this is equal to, of course, mu of XX E 2 times. So if you integrate a function with respect to mu x plus that measure, mu x plus y, that is less than this integral with respect to these things. So this implies if you have x, this implies x plus y is in the domain of integrate mod of square with respect to mu x plus y, that is less than or equal to integrating this with respect to this with respect to this. Yeah, what's the problem?
So from there, E X plus Y, you move to that inequality. How is there a product?
Which one? This product? This which line? This line? Huh?
Yeah.
Here, this is just triangle inequality. P of E X plus P of V Y, norm of that is less than or equal to P of norm of P of E X plus norm of P of E Y.
But why is there a product?
Huh? That's a, no, plus. Where is the product?
Okay.
Plus. Okay. Plus P of E Y whole square. Then you have 2 times that 2AB, which is 2AB is less than A square plus B square, of course. Okay. So that's it. Okay. And we know that P of CX, CY, okay, as a measure for anything, it's equal to, in the inner product, you will get a C and C. Okay, so which is just going to be mod C square times mu of XX as measure itself. So this implies X is in DEF, implies a constant times, constant times X is also in DF. Okay, so all these things, from all these things, we conclude DF is a subspace. We only have to prove its dense. It's a subspace, which is okay. Unfortunately, we have to verify all these things. Okay, it's a subspace, okay, dense subspace. So we have to prove that it's a dense, it's dense. So DF is defined by this. Let's have this definition. Okay. Now So given any x in H, we have to produce a xn in this domain, which converges to that in norm. That's what we have to do. Okay. Okay. So let omega n equal to P in omega such that mod of f of t is less than or equal to n. Is as usual. We make it bounded. Okay. And let x is in. You have P of omega n, which is a projection. Okay. In the range of that. P of omega n h, let x be in the range of P of omega n h. Okay. Then we claim that this x is in the domain. Okay. Then we will prove that P of omega n will increase to 1. Right? Omega n will increase to omega. Okay. And P of omega n will increase to omega. So because of then we have to prove P of omega n x converges to x. P of, omega, it's clear, no? Omega n increases to omega. P of omega will increases to identity strongly, the strong topology. That means you act on some x, it will converge. That's what it means. Okay? That's what we will do. We will look at it. Okay. Okay. So now x is in P of omega n x. Okay. Then of course, P of omega n complement is orthogonal to P of omega n. But I didn't say that. I said this is important. I mean, is it clear? No, wait. Huh?
Don't we need that P is
P is strongly continuous. P is strongly additive, strongly continuous. So if it is increasing thing, it will be strongly continuous. Additivity will imply that. It's a measure theory. I mean, it's a exercise in measure theory. Okay. And I forgot. I mean, see, maybe that follows, but let us just write it. Okay. If E and F are in the definition, if E intersection F is equal to MT, then P of E is orthogonal to P of F. P of F. I think it will follow because it's additive per disjoint set. Okay. Because it has to be a projection. So if you write it, it will follow, but let us just note it. Let us add it. Okay. No, nothing wrong. So P of omega n complement is orthogonal to P of omega n. Okay, they are orthogonal projection. P of omega n is a projection. So that's an orthogonal projection. Okay. Now what do we want to prove? We want to prove that x is in yeah. Now we want to consider integral mod f square d mu xx. Okay. That's what we want to consider. Okay. Over omega. Okay. Now, yeah, mu xx of notice that mu xx of omega n equal to x p of omega n complement, sorry, omega n complement x. This is equal to 0. Okay. Because x is in the p of omega n complement is orthogonal to p of omega n, and x is in p of omega n. So this is equal to 0. Okay. So mu xx of omega n complement is 0. The measure is 0. So this integral is over just omega n. N mod f square d mu xx. Okay. Then this is less than or mod f is less than or equal to n in this set. So this will be less than n square. And that's the integral just mu xx of omega n. Mu xx of omega n. That is less than or equal to n square times non x square. Okay. So this thing imply that x is in domain of f, df. X is in df.
Can you repeat why mu excess of omega n complement is
X is in P of omega n. X is in the range of P of omega n.
Oh,
P of omega n or P of omega n complement are orthogonal by definition. Sure. So because of okay. So now P of omega n. You can look at whichever the way. I mean, okay, you want it that way, so let's look at it. So for general x in h, okay, P of omega n x, okay, which is, you call it xn if you want, minus x arm square, which is equal to P of omega n complement x square, okay, which is just mu, which is just mu xx of omega n complement. That goes to 0 because omega n complement decreases to empty set, and it's a finite measure, so it will go to 0 if you want, whichever thing. It's a theorem. Okay, it's a measure. And of course, it follows from the strong continuity and all that. Strongly countable additive from those things it follows. So we have proved DF is dense. The lemma is proved. Okay. So the lemma is proved. Now we want to define the operator corresponding to any measurable function. Okay. Let's make it a theorem. So F, let's say P is a spectral measure. Spectral measure, and F from, we have omega script F. F from omega to C measurable. Okay. Then there exists a unique operator. Let's call it TF with domain DF satisfying you can take this as the definition of the operator, because an operator, an operator has to take something to something, and that element is given by a linear function. By the inner product, you can define this is equal to y, and TF at x is equal to integral over omega f d mu y x.
What do you mean by f omega to c is measurable?
What do you mean by measurable? It's a function, measurable function.
Okay.
Inverse image of measurable set is measurable. You take a Borel set in R, inverse image should be in the sigma algebra. Okay. So that this it satisfies. See, y dfx gives a number. Okay. So that defines it uniquely, this dfx. So maybe one by one will come. I want to add more things. Let's see what we can do, and then let's not. We'll prove this and come back to the second part. Okay. So proof. Maybe call it 1. Okay. So all we have to prove that it's a bounded linear function. This x, not x, y. Y y going to which one is linear? Y going to this is linear, right? Y dfx is linear. Okay. So there exists, and if we prove it's bounded, okay, then there will exist a z such that this is equal to y z, and you call that z as dfx. That's all. That's all. Okay. So all you have to, this is linear. All you have to prove is we only need to prove. I mean, this if
But why going to that integral is linear?
yeah, correct.
Okay.
I mean, yeah, correct. That's also correct. Yeah, you are right. Absolutely right. Oh, that's what you should correct. There you go. You are right. You are right. So there will exist something. Good. Sorry. You are right. Yeah. Y going to this integral omega. You are right. F d mu y x is linear. Yeah, this is linear. Correct. Good. Now it makes sense. Okay, this is linear. Because this is it. I mean, this is just this. Maybe I should put the TFX on the other side because it's conjugate linear. No, for our. I mean, y going to this will be conjugate linear. No, y or x. You want.
If I go to this is linear, then there is something which, like, it can be represented as y comma.
No, is it the linearity is in, we are using the linear function on x or y?
Should be other way. It should be tf x comma y. Inner product of tf.
Yeah. Then we will get an z, right? So only this is conjugate linear. Okay. If it is conjugate linear, also the same Rees lemma will work anyway. So yeah, I'm just wondering what it's in y, no, not in x. We want the linear functional y. Okay. Our x is in domain of, I mean, x is fixed. Okay. For that we have to do. So we have an x is domain of x. Yeah, x is in df. Okay. And we are getting a linear function. So maybe okay, this is conjugate linear. It's okay. I mean, otherwise you take the bar of that and Rees lemma will work. Okay, this is conjugate linear. So we only so if we prove this is bounded, okay, then I mean as a linear functional is bounded, then there exists z in H such that y z equal to this integral f d mu yx, and define tf at x equal to z. Okay, so all we have to prove that this is bounded. So that's the only thing we have to prove. Okay. So now to prove boundedness, I mean you have to change it. Please, it's okay. I mean, okay, you can understand. You have to change it to conjugate linearity and okay. I mean, it's a bounded conjugate linear functional. You have to prove. That's okay. So all we have to prove is the following. So we have to prove that linear function is bounded. So if I take modulus of integral f d, so here I'm using something in the original, I mean the spectral theorem for bounded operators. To prove boundedness, we claim the following. See, all these proofs which we are going to do in this spectral theorem for unbounded operators, we will be using this set, this omega n, and then restrict it to this. It will be a bounded function. Then we have something for bounded operator. We will just continue to, then we will take limits and apply. Okay. We are going to do it again and again. It will be boring. But so I will leave one of these to you as assignment. And if you can't do it, it's fine. I mean, you should try it. I will leave it to you what exactly is not that much needed for our purpose. Okay. So to prove boundedness, we claim the following. We claim norm mod of integral omega f d mu yx, okay, is less than or equal to. So this is like enough for. Okay, this is less than or equal to norm y times integral over omega mod f square d mu xx. That is xx. Is it clear? Xx. Then whole power half. Okay. So we claim this. So let Fn equal to 1 of the same omega n, where f is less than or equal to n. You hit with this indicator function times f. Okay. Then it is 0 on omega n complement. It is just on omega n, it is f, and omega n complement, it is 0. So it's a bounded function. Is bounded. Okay. Then see, maybe I will give this proof later. Then see, this makes sense. Integral f fn d dp makes sense in the strong sense. See, you can integrate any simple function. It is just addition. I mean, if you have any indicator function 1e, then integral of that over omega is just p of e. 1e, then with respect to dp is equal to p of e. So you can integrate simple functions, which is sum of these things. So if simple function converges, then you can prove that then the corresponding integral, which is a projections, which is in the operators, that will converge strongly to that. Okay. So this thing makes sense. Okay. You call it as TFN. TFN is a bounded operator. That integral will exist in the integral is a limit always. So it exists in the strong topology. It's a bounded operator. This is part of spectral theorem. Spectral theorem for bounded normal operators. Okay. And we have that integral fn d mu yx is equal to, it's actually equal to, by the definition, y of integral fn dp acting on x. See, if you want that, see, yeah, there is something called Bochner integration. So you can integrate it on this integral. You can have the x inside and then you can integrate it. Okay. That will be integral. You are taking that these are function taking values in the Hilbert space, the Banach space. There also you can integrate. But then you make sense. I mean, this is true. Okay. Then if you take the mod, this is less than or equal to norm of y times norm of integral fn dp x. Okay. I mean integral. But then this will be actually equal to, I will prove it later. Okay, if there is time. Okay, spectral theorem, part of spectral theorem. I mean, this is the preparation before spectral theorem for bounded normal operators. Norm y times integral mod fn square d mu xx. Okay, over half. I haven't really said anything. I just said that inequality is true for bounded functions. Okay, which we will prove later. Okay, or you can go through whatever I have done in the videos, then it will be clear. Or you can assume that and continue. Okay. So from these things, this implies that. So now we know that also. Yeah. Now we know that. What do we know? I mean, there is both sides. It is just integral. You can just take the limits. Fn as function, Fn converges to F. Okay. And it's all dominated, and you are fixing a X, and it's all dominated by a single, I mean, F is in L2. F is in L2 of mu xx, which is a, right? That is we have assumed, okay, for X. That we are assuming that X is in the domain of dF means F is in mu xx. Okay. Now Fn converges to F pointwise. Okay. And they are all dominated by this F itself. I mean, if you want Fn minus F goes to 0. Okay. And these are all dominated by this F. So LDCT, Lebesgue dominated convergence theorem, will imply that, this inequality, whatever that inequality, star I called it a star, is true for F. Okay. For a general F. Even though F is just a measurable function, it is square integrable with respect to mu xx. So we can use that, and that then inequality is true. Okay. No, yeah, this inequality is true. Yeah. Where is that inequality? This inequality is true. And further, for all this Fn, for all Fn, I mean, let me just state it and I will make it clear later. Okay, because I'm using that for all Fn, which is bounded for bounded function, T Fn x is equal to integral mod Fn square d mu xx, okay, power half. The norm is attained. This says that the norm of Tfnx is less than or equal to that, right? See, we have that. If you define this as the Tfn acting on X, okay, that will imply that is the Tf. See, that is true for F. I will write it again, sorry. And that says that Tfn exists, Tf exists, and Tf at X norm of this is less than or equal to integral F square d mu xx. Okay. But Tfn minus Tf, okay, acting on X, which is equal to norm square. If you just take it, this is equal to Tf. I'm sorry, I'm making too confusion, but further it is true that norm of Tfn x square. This is, please assume this. This is equal to norm Fn square d mu xx. Okay. Of course, F1 converges to F in L2. So notice that domain of Fn is H. Okay. And domain of F is equal to domain of not Fn, Tfn. Okay. Domain of T domain of Tf, which is equal to, which we call it as Df. Okay. And domain of Tfn equal to Tfn, Dfn is everything because it's bounded. Bounded function with a finite measure is integrable, so it's everything. Okay. And domain of Tf minus Fn, that is equal to domain of Tf. So you are just, if something is in domain of F, okay, so domain of Fn is everything. So domain of F minus Fn will be integrable for that x, right? Is clear, right? So these are equal. Okay. Now if you just calculate Tfx minus F is in Tf, Tfx minus Tfn x, okay, which is actually equal to Tf minus Fn. It's actually, we just go through the definition because it's through the integral, no? You have an integral F. Okay, F minus, it is just F minus Fn, right? F minus Fn. Okay. Square. And this is equal to, they should go to 0. You got lost. And I'm also getting, I'm getting, yeah. So this is just omega in complement, right? No, so yeah, it is just, yeah, it is just the integral over in omega n complement of of the same F mod F square, right? No, this will not be same. No. I just want to prove this. No, why is this true?
Because F is equal to Fn on N.
No, this is just the more. You want to tell? No, this is just the norm. We are defining it through the we are defining it through the integral. No, I am just trying to prove that norm of Tfx is exactly equal to the square, that square. That holds for all bounded things. Okay, so I want to prove that it holds for any F. Okay. So see, we have that Tfnx is, we have that norm of Tfx is less than or equal to norm. I mean, this inequality is satisfied, right? This inequality is satisfied. Whatever this inequality we have here, This inequality imply that from this inequality, we have that this implies that norm of Tfx is less than or equal to that integral mod f square d mu xx, okay, power half. I mean, I have written it here. Here I have written. Okay. This is less than this, which follows from this inequality, right? It is defined as a linear functional, okay, and linear functional is bounded. It is bounded by this. Okay, I want to say the norm is attained. That's what I want to say. Okay, now I'm talking about Tf minus Tfnx, okay, which is equal to Tf minus fx. Now this is less than or equal to, we know that f minus fn square, okay, d mu xx. Okay, now this goes to 0. I mean, this is the right argument. This goes to 0. So this implies Tfx goes to Tfnx. Okay. In particular, norm of this will go to norm of this. Okay. This goes to this, right? I mean, the difference goes to 0. So this goes to this. The norm of this will go to this. So, but we know that norm of Tfnx is equal to, this is from the bounded spectral theorem, is equal to integral over omega norm fn square d mu xx whole power half. Okay. So because of this conversion, we get that Tfx is also equal to integral over omega norm f square d mu xx square root of half. Okay, it is just the norm of Tfx is just the L2 norm of f with respect to d mu xx, which is a positive measure. Okay, any doubt? See, we defined Tfx, the value of Tfx as a linear functional. So by Rees lemma, we got some vector z, and that's a bounded. We proved that that is bounded, and the norm is bounded by something which we proved. But the norm is attained for finite bounded functions. Okay, but since this goes to 0, see, the point is Tf minus Tfx minus Tfn is again a T of some function. So that is also bounded by some L2 norm of f minus fn square, which goes to 0 as functions. Okay, so because of that, but then the norm is attained for all the bounded functions, so it should be attained for this also. Okay, norm means not norm of the operator. Operator is unbounded operator. It is norm of Tfx. Okay, that is equal to this. This is okay. This proof is okay. 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 So this is what I. So then what do
You mean TFNX goes to TF?
Tfnx goes to Tfx. Yeah. Where did I write? Tfn, correct. Yeah. I will written the other way. Yeah. Tfnx goes to Tfx, not I mean, constant cannot go to the. Okay. Okay. I have to prove that this is self-adjoint. I want to prove that Tf star is Tf bar. I don't think I can finish it in 10 minutes. So I will stop. I will recall if there is a problem also, I'll go through and then recall the whole thing again. It's better to, I mean, we don't, rather than the proof, we have to understand the spectral theorem clearly, how these operators are defined and all those things. Okay. So I will go through it again and then prove the rest of the proof. That is, I mean, rest of the theorem, which I haven't even stated. Tf star, this is a self-adjoint operator. This Tf, sorry, this is not self-adjoint operator. Tf star, this is a closed operator. Tf star is equal to Tf. So since it is star of something, it will be a closed operator.
Yes, TF bar.
Tf bar, right, sorry. Tf star equal to Tf bar. Okay. It will be clear that Tf bar, it's easy to prove Tf bar is contained in Tf star. It's easy to prove. I mean, you have to prove that the inner product condition. Okay. It's clear. Let me write it. If you have some y, Tfx, okay, x is in Tf, x is in, okay, let me just prove this and start. So we have, so the second part is Tf star is equal to Tf bar, okay. So notice that df is equal to df bar, of course. Okay, because df is defined through some integral mod f square, and it doesn't matter whether you take f or f bar. Okay. Okay. So now if x is in df equal to, of course, df bar, okay, then t and y is in y is also in df, okay, then x y here y df at x equal to, we have defined it through integral f d mu yx, right? D mu yx. Okay. Now this is equal to bar of integral f bar d mu yx bar, which is xy. Mu yx of any e equal to y p of e x, okay, which is equal to p of e y x, okay, which is equal to bar of x p of e y. Okay, so you are just integrating f bar with respect to d mu xy. Okay, now this is equal to this is equal to what? This is equal to x tf bar y, which is equal to bar, which is equal to tf bar x. So ytf, we started with ytf x, which is equal to this. So this, it is just this equation imply that tf bar is contained in tf star. This is precisely the meaning of tf bar. We started with ytfx, the inner product ytfx, and we ended up with tf bar yx. This means tf bar is contained in tf star by the definition. We only have to prove the domain matches. Okay, again we have to go through these finite approximation and all that. Okay, so we will do it in the next class.